All right, here is the general theorem. Right? So suppose that we have a second order, a linear ordinary differential equation that is non-homogeneous, so that there is a right-hand side g of t. So then the theorem tells us that its general solution can be expressed as some particular or specific solution of this equation plus this form, and this form is nothing else but the general solution of the corresponding homogeneous equation, right? Now, this theorem is exactly the same as a similar theorem from linear algebra 1 about solving systems of algebraic linear equations. And I hope you still remember how to prove it and what the theorem is about, but I also understand that it was a long time ago, so it's not going to do any harm if I prove it again for you. It's nice and simple. So let me prove it, okay? To prove this theorem, we need to do two parts. So the first part is we need to show that any function of this form is a solution of this differential equation. So let's do it. So suppose that our function y is expressed as y capital, which is a particular solution of the non-homogeneous equation, plus c1 y1 plus c2 y2, where y1 and y2 are not linearly independent solutions of the homogeneous equation. And so let us just substitute it to the our non-homogeneous equation. So then y double prime plus p y prime plus q y equals is y capital double prime plus p y capital prime plus q y capital plus c1 times y double prime plus p y prime plus q y1 plus c2 y double prime plus p y prime plus q y2. Well, but then notice that this is, we know that y capital is a specific solution of the non-homogeneous equation, so it means that this is g. But then y1 and y2 are solutions of the homogeneous differential equation, which by definition means that this is 0 and this is 0. And then therefore we get y double prime plus py prime plus q y is g of t, which is exactly what this part is about, right? So we were supposed to show that every function of this form is a solution of this non-homogeneous equation. So conversely, we need to show that every solution of our non-homogeneous differential equation, so suppose that we have function y, and we know that y double prime plus py plus prime plus q y is g. So we need to show that our function y can be expressed in this form. It is y capital, which is a specific solution, plus c1 y1 plus c2 y2. Okay, so let's just write. So y equals, since we're supposed to have y capital, we'll just write it. Well, but then in order for this to be a correct equality, we just need to complete it. So it's plus y minus y capital, right? So this is our y, our particular solution. So what we need is to verify that this part is a solution of the homogeneous equation. Is it true or not? So let's try. So y minus y capital double prime plus p y minus y capital prime plus q y minus y capital. Well, but this is just g minus g, which is 0, so it's true, right? So this y small minus y capital is indeed a solution of the corresponding homogeneous equation, which means it can be expressed as a linear combination of basis solutions. So the theorem is proved. Okay, here is an example. This is a non-homogeneous differential equation with non-constant coefficients. Well, strictly speaking, there is no general way to solve it for non-constant coefficients, but it's just that I know that the two solutions are t squared and t cubed for the corresponding homogeneous equation. It's just because I designed this differential equation that way. So you can imagine that this is a lucky guess. But suppose that we were given this information, then at the same time we can try to guess some particular solution of this differential equation. And well, what we can do, since the right hand side is constant, so we can try constant, and we realize that the constant should be 1/6. So it is a bit of a guessing too, but it means that once we know this information, then the general solution of the non-homogeneous differential equation is just like this, is a particular solution of this non-homogeneous equation plus the general solution of the homogeneous equation. Yeah, and this part is a bit unusual in the sense that the quiz is in the middle, so you can probably pause the lecture and do the quiz, or maybe you can wait until I finish and do the quiz, but there's not much left here. All right. So when we need to solve a non-homogeneous differential equation, a linear differential equation, then there are two methods to do it. So the simpler method is called the method of undetermined coefficients, and basically it is kind of guessing. It is not a general strong method in the sense that it's not a well-defined procedure. So sometimes it works, sometimes it doesn't. But if it works, then the answer is kind of simple. If it doesn't work, then, well, it just doesn't work. The alternative is called variation of parameters. And in the remaining part of today's lecture, I'm going to explain variation of parameters. It is a very, very complicated method, but it has some very beautiful ideas, which is why I really want to explain it. And another thing is variation of parameters is a general method, so it works all the time. So if you just give me any crazy functions, variation of parameters is going to work. The method of undetermined coefficients isn't going to work. But still, you are encouraged to read about the method of undetermined coefficients in the textbook and try to apply it to solve the general solution of this differential equation that I'm going to explain in the next part, well, in the next few parts of today's lecture.